Have you ever stopped to think about how scientists keep track of the millions upon millions of different molecules that exist? I mean, it sounds like it should be absolute chaos, right? But it turns out there's a surprisingly elegant system behind it all, a universal language for chemistry. So let's get into it.
Right, this is the central puzzle. It's kind of like trying to build a giant complex machine where every single nut and bolt has a dozen different nicknames depending on which mechanic you ask. It would be impossible to get anything done. For decades, chemistry faced this exact problem, and the solution that finally emerged is just brilliantly systematic.
You know, back in the early days, chemists basically named compounds based on where they came from. Formic acid, for example, was named after ants. Formica is Latin for ant because, yeah, you could actually distill it from them. And citric acid, you probably guessed it, comes from citrus fruits. Now, these names are kind of charming, but they tell you absolutely nothing about what the molecule actually looks like or how it's built.
So, this all led to what you could really call the era of naming chaos. And it was a huge roadblock for science, making it incredibly difficult for scientists to communicate their discoveries and build on each other's work.
I mean, just imagine it. A chemist in Germany discovers a new compound, and at the same time, a chemist in France discovers the exact same molecule, but gives it a completely different name. How could they ever figure out they were working on the same thing? This wasn't just confusing. It slowed down progress and could be genuinely dangerous.
To solve this massive problem, the entire global chemistry community came together to create a universal standard. And this brings us to the hero of our story today, IUPAC.
That's the International Union of Pure and Applied Chemistry, or, IUPAC for short. They stepped in to create a universal rulebook, and the goal was simple, but at the time, it was revolutionary. Create a system where any chemist, anywhere on Earth, could read a single name and draw the exact same molecular structure. Zero ambiguity, zero confusion.
Honestly, this is the perfect way to think about it. The IUPAC system isn't just a big dictionary of names, it's a grammar. It has rules for prefixes, roots, and suffixes that you piece together to build a name, just like you'd build a sentence, and that name tells you the molecule's entire story.
So, how does this grammar actually work? Let's break it down and decode a chemical name piece by piece. I promise it's a lot more logical than you might think.
Okay, so the foundation of any organic compound's name is its main carbon chain. You can think of this as the molecule's last name. The IUPAC system uses these specific prefixes to tell you exactly how many carbons are in that main chain. 1 carbon is meth, 2 is eth, 3 is prop, all the way up to 8, which is oct, and it keeps on going.
Let's start with the simplest kind of organic molecule, an alkane, which is really just a chain of carbon and hydrogen atoms. Naming one follows a really simple 3-step process. First, you find the parent chain. That's the longest continuous string of carbons. Second, you number the carbons in that chain. And third, you identify and name any branches that are hanging off of it. Let's give it a shot.
All right, here's our molecule. Step 1, find the parent chain. If you trace the longest continuous path of carbons, you'll count 8 of them. The prefix for 8 is oct, and since this is a simple alkane, we add the suffix ane. So that gives us our parent name, octane. Easy enough.
Now for step 2, we have to number that 8-carbon chain. And the rule is you always start from the end that gives the branches, those little parts sticking off the main chain, the lowest possible address numbers. So if we count from the left, our branches are on carbons 3 and 6. But if we count from the right, they're also on 3 and 6. That's a tie. So what do we do now?
Well, the tiebreaker is surprisingly simple. It's the alphabet. Let's look at our branches. We have a 2-carbon branch, we call that an ethyl group, and we have a 1-carbon branch, that's a methyl group. Since E for ethyl comes before M for methyl alphabetically, the ethyl group gets the lower number. And that means we number from left to right, putting the ethyl group on carbon 3 and the methyl on carbon 6.
And now we just put it all together. We list the branches alphabetically, each with its number, and then stick the parent name on the end. And that gives us 3-ethyl, 6-methyl octane. See how that works? It's not just a name, it's a precise blueprint. It tells any chemist in the world exactly how to build that molecule from scratch. That's the real power of the IUPAC system.
But of course, molecules are more than just simple carbon chains. The real beauty of the IUPAC language is how it expands to handle molecules with more interesting features, the parts that actually give them their unique chemical properties.
These properties are determined by what chemists call functional groups. A functional group is basically the active site of a molecule. It's the part that dictates the molecule's chemical personality and determines how it's going to react with everything else. So how does this system handle these? It's actually brilliant. A functional group usually just changes the suffix, the ending of the parent name. For instance, adding an alcohol group, an OH, changes the end of the name to all. A ketone group changes it to 1. It's like adding a verb to our chemical sentence. It tells us what the molecule does.
And this right here is a perfect example of why that precision is so important. Look at these two molecules. Both have a 3-carbon chain, so prop. Both have an alcohol group, so they end in all. But that single number tells you exactly where that group is. Propan-1-ol has the alcohol on an end carbon, while propan-2-ol has it right in the middle. You probably know propan-2-ol by its common name, rubbing alcohol. A single digit in the name describes two completely different substances. Details matter.
So you might be thinking, okay, this is clever, but why do we care so much about this level of detail? Well, because this universal language has a massive, direct impact on our health, our safety, and our technology every single day.
Seriously, this precision is absolutely critical. In medicine, the difference between two very similar molecules can be the difference between a life-saving drug and a dangerous poison. In research, it ensures a scientist in Tokyo can perfectly replicate an experiment done in Toronto. It allows for clear safety regulations on hazardous materials. It even lets inventors patent one specific molecule, protecting their discovery. This isn't just some academic exercise. It's the bedrock of modern science.
The IUPAC system is just such a great example of the power of creating a clear, logical, and universal language to make sense of a really complex world. And it really makes you wonder, if we can manage to do this for millions of molecules, what other complex systems in our world could benefit from a truly universal language? That's definitely something to think about.